Hi scholars, I hope you're all having a wonderful day today. Today we are going to be moving on to our next lesson in this unit, lesson 5, on predicting the behavior of charges. So for today, you are going to need your notebook, pen and pencil. Some of you might need a calculator. We're doing some simple calculations, but having a calculator at hand might be helpful. And then the tabs open, you should have your Google Classroom, and then also just the classwork document for today. Before we start our lesson, I was reflecting on something yesterday. So yesterday I had posted a picture, I put a picture of Coulomb, the French physicist, on the classroom slide, on the classwork slide. And I was thinking to myself, like, wow, like I wonder, like most of the people that we learn about in science, like all these things that we've, a lot of the different things that we learn about are named after the scientists that discovered them. And in the great majority, they're all white European men. So I was thinking to myself, like, what is the statistics of people of color who have won the Nobel Prize in physics? So the Nobel Prize, if you don't know, is a very prestigious prize that comes out of Switzerland that's given every few years in many different areas, in physics and economics and chemistry, all different sciences, Peace Prize as well. Those tend to be the most popular, like Barack Obama won a Peace Prize a few years ago, Martin Luther King, Nelson Mandela. So we've heard of the Peace Prize most commonly, Malala also a few years ago. But we don't hear so much about physics. So how many people of color, both either Latino or Black, have won prize? Guess. 0. But there is hope. You all are the future of science. And like personally for myself, they feel like unrepresented as a Latina woman, to not have a single person, not a single Latina woman to have won a prize like this can be a little disheartening, but what's hopeful for me is that we are working together to be able to create like a group of scientists, of young scientists like yourself, who can grow up to break the barriers of research within science. Right, so this is just a little picture of my AP Physics students working hard when we were still in school. All right, and because of this, I also want to start highlighting some scientists of people of color who have become predominant scientists in their fields, but that might not have won these like most prestigious prizes. But so we'll keep out an eye on that for the future. All right, so coming back to today's lesson. Our agenda for today, we're going to model one of the problems from our exit ticket from yesterday, and then we're going to go over some key points, a quick check for understanding, discuss a core idea that you'll need for the independent practice. So in previous lessons, we learned about the relationships expressed in Coulomb's law and how the size of a charge and the electrostatic force have a direct relationship, right? So we learned that yesterday. And that the distance between two charges and the force have an inverse square relationship. Right? So that is governed by the equation of Coulomb's law that's on the screen right now. Today, we are going to apply these concepts to different scenarios by ranking the electrostatic strength of the two objects based on Coulomb's law. So just as a reminder, pay attention to these previously mentioned relationships while we're practicing today. If you need for yourself as a reminder to have this equation, well, you should have this equation written down in your notebooks, but we'll be using it today. All right. So let's start today with a model from yesterday's due now. All right, sorry, yesterday's exit ticket. Okay, so this is at the very beginning of your classwork document. It is meant for just a reference for you, but I would like you to draw out what I'm writing in your notebook. Not in your classwork document, but in your notebook so you can have this as a reference for the future. Okay, so we have here 3 diagrams. So it says the diagrams show 2 charged objects and their separation. Rank the force and the object rank the force that the left object exerts on the right object from strongest to weakest. Explain how you made your ranking. All right, so we have our 3 charges. So the first thing that we would approach is for each one of these, we're going to find what the force is, and then we'll rank them. Just as a reminder, I'm going to write it here on the side. My equation is the force is equal to this constant k times the 2 charges divided by the distance between them squared. Right, so even though we don't know what all of these different quantities are, we can still just go by the different coefficients of the different values. So here, if there's nothing in front, we just assume that this is 1. So it's a coefficient of 1. So we're going to look at these different coefficients and see which one would have a greatest force. So for this first one here, if I plug in those, just the coefficients into my equation, I have k, so 2 times q times again 2 times q, and these are both positive. And I'm dividing it by the distance between them, which is just d. So that would be d squared. D or r are interchangeable in this case because it's distance, or sometimes referred to as radius. So then here we have 2 times 2, so that's going to be 4 times the original force in this case. Right, so this is for 1. For 2, we have a coefficient of 3. Times just a charge, and then, well, k. And then divided by the distance squared. So in this case here, I have a 3 times a 1, so that's going to be 3 times, and then my original force. And then the last one here, my coefficients are just 1. So for 3, I have q times k divided by the distance squared, which is just going to be equal to, there's no additional coefficients here outside of the number 1, so the force is going to be equal to the original force. So this tells me here that the largest force is going to be happening by number 1. Right, and then the second strongest is 2, and then the third strongest is 3. Right, so that's my ranking. So again, we're just doing algebraic manipulation here. We've done problems like this before in the past, where we're just looking conceptually at how different quantities relate to one another by doing rankings. All right, so now take time to write this into your notebooks. You can press pause if need be, and then we're going to move on to the second problem. Okay, so for the second problem, I'm going to give you the answers. So here I see for my coefficients, right, they're all equal. They're all equal to 1 here. So my force is just going to be equal to kq divided by r squared. So my original force is just going to be equal to, it's just 1 times the original force. And then over here now I see there's a 2 in my denominator. So how would I solve for that? My force now is going to equal to k times the 2 charges. And then now I'm dividing this by 2d, but then this whole thing gets squared. Since the whole thing gets squared, then that means that this 2 here also gets squared. So 2 squared is equal to 4. So then now I have this 1/4 coefficient here that comes out. So that's a k times my 2 charges divided by the distance squared. So now I have here that my force is 1/4 of the original force. And yesterday, in this previous slide, I'm going to go back. Here we're saying that as the distance doubles, the force drops to 1/4. This coincidentally ends up being the same number from the example that we were just doing. But the larger, like further away your particles are, the less force there's going to be. And the closer your particles are, the more force there's going to be amongst them, right? So that makes sense here in our response, that the larger the distance between them, the smaller the force, because now my force is just a fourth of the fraction of the original force. And then the same thing happens here, where now I have my distance is tripled. So then I'm going to have a 3D in the denominator. I'm skipping writing the numerator because it's the same, because the charges are equal to 1. So then if I square 3, that ends up being 1/9. So by making the distance 3 times as large, my force is decreased by 1/9. So then that means that my ranking is going to be actually coincidentally the same as before. 1 is the biggest, 2 is the middle, and 3 is the smallest force. Right, if you have any questions, write them down. You can ask your teacher at the end of the video. Right, again, take your time to write this down. If you don't recognize this, this was a problem that you did yesterday also in your exit ticket. All right, so a key point when we're solving problems like this, we're going to be comparing the magnitude of the electrostatic forces of the point charges. So it's helpful to use algebraic reasoning. Since the charge constant doesn't change, that means K, we can compare the charges, the magnitude of the charges that do change, right? So the charge itself doesn't change, it's just the magnitude. So we're looking at the, just like the algebraic reasoning to solve these problems. Make sure to write this in your notebooks actually, so that you can refer back to it as you're solving. Because we're gonna solve some more problems about that that look just like these. So if this is helpful for you, please write it down in your notes. Okay, so now let's do one more quick check for understanding. On your own, which one of these scenarios of charged objects will have a stronger electrostatic force? So take the next 2 minutes to figure out which one of these has the strongest electrostatic force. Please answer this in your classwork document. You can press pause now and then press play when you're ready to come back. Press pause now. All right, welcome back. So let's check out your answers. So for here, we recognize now that the coefficients here, so is just, well, it's 1, and then here it's also 1, and then to here it's also 1. So my force is just equal to like the total force of the equation, right? Which is K over d squared. Over here, we have a whole bunch of different coefficients that we're going to have to take into account in our algebraic reasoning. So let's look at that. So now my force is equal to constant K times 3Q times 3Q divided by 1/3 the distance squared. So now we're just going to multiply all of the different coefficients that are here. So 3 times 3 is 9. 9, and then I'm going to keep my variables over here. And then now I'm going to square d and 1/3. So I have 1/3 squared is 1/9. And then times d squared. So now I have a fraction in the denominator. I recognize that this might be a challenging thing for you guys. It's been, but I think you should all have the mathematical skills, like you've learned how to solve these in algebra already. So just here on the side, I'm going to make a note. When you have 9 divided by a fraction, which is 1/9. So the way that you solve this is you bring you can bring this fraction over to the side like this, 9 divided by 1/9. And then when you are dividing a fraction, you can multiply it by the reciprocal. I think that's how you guys learn how to do this. So the 9, this ends up becoming 9 times the reciprocal of 1/9 is 9, right? Because you reverse it. So then 9 divided by 1/9 ends up actually being 9 times 9, which is 81. So then my force here is going to be 81 times the original force. So this makes sense for us because the larger the force, right, the larger the charges. So here there's a charge of increase of 3 on both sides. My force is going to become larger, and then also the closer something comes together, the stronger the force is going to be. So it makes sense that it's increasing by this much. Okay, take a second to write that down into your notes as well. Okay, so a core idea. When you're solving questions that deal with electrostatics, it's important to remember that even if we don't have the exact values of the charges of the distance, like in the examples that we just did, we can still compare the magnitude of the electrostatic force between the charged objects. So we're going to be doing this by inputting the multipliers from the problems into Coulomb's law. And that's just like a fancy way of explaining what we just did in the previous 3 examples. So for our independent practice today, you are going to take the remaining time in class to complete the practice problems in your classwork document. Complete all the work in your classwork document and submit it by the end of the day. If it's helpful for you to do things in your notebooks or on scrap paper, then feel free to do that and just transfer your final answers and your reasoning onto the classwork document itself. Okay, I hope you all have a wonderful and fantastic day, and I'll see you tomorrow.